Hi everyone, in this video we are going to learn about self-excited DC motor. In our previous video we have already gone through separately excited DC motor and also through the derivation of torque equation, which will be useful for plotting the graphs in this self-excited DC motor. See, in this self-excited DC motor, firstly, coming to this types of motor, you will have AC and then DC. And now coming to the DC motor, you will have self-excited DC motor and then separately excited DC motor. So generally we use self-excited DC motor. Separately excited DC motor will not be used more because in this case of separately excited motor, the motor will run dangerously at a high speed when there is no back EMF. And now coming to the self excited DC motor, it is further classified into three types, that is your shunt motor, series motor and then compound motor. And this compound motor is further categorized into cumulative motor and then differential motor. So now let us discuss what is shunt motor, and in next video we'll be learning about series motor and then compound motor. So now coming to this video, so in this shunt motor, this is how it looks like. Here your field winding is exactly opposite to the armature current. It means your field winding and armature should be connected in parallel when it is in the case of the shunt motor. So in the case of shunt motor, field winding and the shunt motor should be connected in parallel. Okay, and in this shunt motor, here see, you are having a voltage V, and let us suppose a current I is flowing, and here you have a field resistance, that is field winding, and the current flowing through this field winding, let us suppose it to be IF, and the resistance as the field resistance RF, let us suppose it to be RF, and here through the armature the current flowing, let us suppose it to be IA, and the armature resistance as RA, and here you will be having a back EMF which should be exactly opposite to the supply voltage. Okay, and now coming to this, here your field resistance should be greater than your armature resistance. Here you may get a doubt why the field resistance should be greater than the armature resistance. See, whenever the field resistance will be greater, only small amount of current can be flown. We know that V is equal to IR, right? And I is equal to V by R. It means whenever your resistance is high, current should be low, and whenever your current is high, resistance should be low. So when your field resistance should be higher, in that case only small current will flows, so that a small current will gives you stable field. Okay, only small current flows, and stable field current will gives you the constant flux. Okay, stable field current will gives you constant flux. So because of that reason, your field resistance should be greater and your armature current resistance should be lower, because through your armature resistor more current should be flown, because this more current will only produce you the greater torque, right? And whenever your torque is like greater, it will mechanical work, it will do some mechanical work, right? So since we know this relation, torque is directly proportional to flux into Ia. So if your Ia, that is if the current flowing through armature is greater, then only the torque will be greater and will get a good output, like a better work is done, right? So your armature resistance should be lower and your field resistance should be higher. And here is an important point, that is field winding should be thin with more number of turns. So field winding should be thin means its area of cross section should be lower and its length should increase. Okay, since it should contain more number of turns, right? So its length should be increased. So your field winding should be thin with more number of turns. Only in that case your field resistance will be higher, right? And You may get a doubt now. Where do we use shunt motor? Only it was used when there were applications which requires low torque and constant rotating speed. Only when you needed low torque and constant rotating speed, in that case you will use this shunt motor. We will discuss about those examples later. See, for lower torque and constant speed applications we will use this shunt motor. Okay, and here is an important point. See, to reverse motor rotation, so in order to reverse this rotation of motor, we have to either reverse the field winding connection or else armature connection. Okay, either reversing the field winding connection or this armature connection will only leads to the like reversing the rotation of this motor. Okay, only in that case it will be reversed. And this field winding should be connected exactly opposite, that is in parallel. We have discussed this already. And the field current is constant. The moment when the field current is constant, then your flux will also becoming constant. Okay, since we know that the flux is directly proportional to I from this Faraday's law. Like in the case of inductor, we have discussed that flux is directly proportional to the current. Okay, so when the field current is constant, then your flux will also become constant. And now here you have graphs. See, we know this equation that torque is directly proportional to flux into Ia. Since your flux is constant, now your torque is directly proportional to Ia, right? Which means we can write torque is equal to K into Ia. It is in the form of Y is equal to mx. If any equation is in the form of Y is equal to mx, it should be a graph which should start from the origin, right? So torque versus Ia graph will be of straight line starting from the origin. So this is how you get this graph. And now how can we plot a graph between, let us see, for N and Ia? You may get a doubt now. See, we know that, see, from this equation we can see that N is directly proportional to Eb by flux. Since our flux is constant, we can simply write this equation as N is directly proportional to Eb. Why? Your flux is constant, right? So N is directly proportional to Eb. But we know that Eb is equal to V minus Ia Ra, right? So your N will be directly proportional to V minus Ia Ra now. But or else you can simply remove this step. We know that Eb is equal to V minus Ia Ra, right? And here we have chosen your armature resistance should be in a very less quantity, in a very minute quantity. So if you multiply anything with a minute quantity, it will also become minute, right? So you can neglect this term totally. Okay, so your Eb will be equal to V. That means your speed will also become constant. As the moment your speed becomes constant, your N is also directly proportional to Ia, right? Since this is constant, now your N is directly proportional to this V, and since your speed becomes constant, this graph should be constant, but it gets slightly varied because since this armature resistance may be minute, but if the current quantity is very high, then it will show some slight variation, right? So it will get slightly deviated. Okay, and this relation between N and Ia is in this way. So we know that torque is directly proportional to flux into Ia, but your flux is constant. That means torque is directly proportional to Ia. And in the same way we will get N is also directly proportional to torque, right? So if the relation between your N and Ia is in this way, then your relation between N and torque should also be in this same way, right? Hope you have got the connectivity. And the examples where we use is for the low torque and high constant rotating speed. So the applications which require low torque and constant rotating speed there we use shunt motor, and its examples are centrifugal pumps. See, if you can see like a pump, so through a pump, if a steady flow of water should be flown, so for the steady flow of water should be flown, like with a constant speed it should flow, and your torque should also be less, right? So in the case of your centrifugal pumps you use shunt motor. And in the same way, like in conveyors, in some fans, some blowers, elevators, we use this shunt motor due to their excellent speed regulation. So in fans it should be rotating with a constant rotating speed, so in the fans we can use this shunt motor, and due to their excellent speed regulation and moderate starting torque. Okay, so this is about all about shunt motor, and it is more than enough if you mention all these points when in examination they were asked, if they ask you to write about shunt motor. And in next video we will be going to discuss about series motor, and stay tuned for the next coming video. If you have any doubts regarding these video, feel free to ask me in comment section. Thank you for watching, and subscribe my channel for more videos.